Well, let me say that it's a great pleasure for me to be here. Thanks, Graham and Felix, for the opportunity to give this tutorial. Well, my goal is trying to tell you a little bit about what we are doing with ultra-cold matter towards the exploration of many-body physics and how we are trying to connect all the interesting directions in quantum information. My talk is also going to be a little bit self-centric in the sense that I will focus a little bit more on what is going here at GILA. Hopefully it helps as an introduction of Jun's Jet talk in a plenary talk later during the week. And yes, so hopefully I can provide some excitement and you gain more interest in learning what is happening in this field. All right, so we are talking about cold quantum matter. So I think if we are talking about, oh, sorry, I am looking at the wrong, it's the second part. All right, so if we are talking about ultra-cold matter, let me define what it means for us, ultra-cold. So for that, let's have a thermometer, let's have a temperature scale, and we know that at room temperature, what is happening is the atoms in the air are moving extremely fast. So they're moving about at the speed of sound, 300 meters per second, and if we want to control these atoms, it's going to be very difficult. So in order to control and take advantage of atomic systems, we want to cool them down. And the question is how much we have to cool them down to make them useful for us. And if now you think about the coldest temperatures that you naturally find in nature, you might think is the temperature of the outer space. That is kind of comparable with the temperature at which, is this working? Maybe I will have. This is the temperature at which helium condenses. That is of the order of 4 Kelvin. And what happens is that this is, okay, here. Even at these temperatures, the atoms are still moving very fast, 90 meters per second. So in order to make them controllable, what we had to cool the gas is down to 10 to 100 of nanokelvin, like a billion about the absolute zero. And in this case, we were able to, at these very, very low temperatures, we are able to actually control a race between 10 to the 4 to 10 to the 6 atoms at very, very low densities, like 5 orders of magnitude more dense than air. And at these conditions, we can reach velocities that are of the order of centimeters per second, and then we can control and manipulate these atoms in the lab. So this record or this kind of temperatures cost a lot of effort, a very successful and rewarding effort, and actually was recognized with 2 Nobel Prizes. One in 1997 was given to Stephen Chu, Cohen Tanuji, and Bill Phillips. And what they show is that using lasers, you can cool down the atoms to microkelvin temperatures. So basically you have your atoms and then you illuminate the atoms with laser light. And then you bombard the atoms with photons. And by bombarding the atoms with photons, you make the atoms slow down. And you can trap them, reaching records of temperature of microkelvin. But this temperature was not enough actually to reach the condition of quantum degeneracy, when atoms become really, really quantum mechanically, and they are ruled completely by the laws of quantum mechanics. And for that, you had to cool them down further to around 100 nanokelvin, and this was recognized, and it was one of the Eric Cornell and Kai Wyman at work here at GILA, Wolfram Ketterle at MIT, and they were able to reach temperatures of this order of 100 nanokelvins, where the systems cooled down and reached the condition of quantum degeneracy. So here, quantum statistics matters, and if you are bosons, all the atoms start to condense all to the ground state, forming a new state of matter that is called Bose-Einstein condensation. And I think this Nobel Prize was recognized in 2001. So just to give you a taste of what are the tools that we use to control the atoms and to bring them to quantum degeneracy and it's going to be a powerful trapping tool that is going to come up many times in my talk, is the idea of optical lattices. The optical lattices we use them to create artificial crystals of light. What is the idea? The idea is that we take our atoms and we illuminate the atoms with laser beams. And what happens is that in the presence of light, atoms feel a force that are proportional to the intensity of the laser beams that we use to illuminate the atoms. And if we use two counterpropagating beams, you know that they can form a standing wave. So this is the type of potentials that the atoms are experiencing, and therefore they can get trapped in these wells. And with that, for example, we can resemble the behavior of electrons in a solid state crystal. So the advantage here is that this periodic potential is created by light. So it doesn't have any impurities, it's perfect, it's controllable. We can change the dimensionality, we can change the depth of the potential. So it's a very powerful tool that we have used to control and manipulate the atoms. So, but maybe you are just sitting there and thinking, well, we have ultra-cold matter. And maybe the question that you are asking yourself is, what can we do with ultra-cold atoms? And we can do many things. But today, one of the topics that I'm going to focus is how we are aiming to use this ultra-cold matter for understanding complex quantum many-body systems. What is our scientific vision? What is what we want to achieve? So what we want to do is that we want to harness many-body quantum systems and use them for applications ranging from quantum information to metrology. We want to create very, very precise sensors. And how we are going to do that? Well, the problem is that many-body interacting quantum systems are extremely complex. They are really hard to understand and manipulate. So what we are trying to do is trying to use the tools of amophysics to bridge the behavior of few-body systems that we know how to control and manipulate, trying to bridge this huge gap and then trying to understand the behavior of complex many-body systems. So how we are going to do that? Well, the fact is that in AMO, we have these ultra-cold systems that offer us very well understood microscopics. What does that mean? That if I write a Hamiltonian in a paper, this is exactly the Hamiltonian that is describing my atoms. It's not like in condensed matter systems when the behavior is so complicated, so complex with disorder, with imperfections, that the Hamiltonian is not exactly, but it's just an abstraction that generically describes the system. Here, we really, really can write with specific parameters the Hamiltonian of our model. And moreover, it's not only that we can write it, but we can control the parameters even during the course of the experiment at will. And therefore, we have access almost in real time to quantum dynamics. This is, for example, not the case of solid-state systems where we need femtosecond lasers, because the behavior is so fast that it's very hard to see in real life. Here, in condensed matter systems, here we have the possibility to really track and understand how the system is evolving. So it happens that we are learning to control the atoms so well that we are masters. We have been masters now in controlling independent particles. That's what we have learned now. And these have led us, or what we are, the type of systems that we are able to control is not only simple atoms that have one outer electron, that were the first one that we were able to cool down. So this, in 2001, when the Nobel Prize was given, the first condensation in 1995, were atoms in the first column of the periodic table that behave very similar to hydrogen, very simple. And with that, we were able to create boson Fermi gases of these systems and trap them in a continuum. But later, we learn how to trap these atoms in optical lattice and try to emulate more the behavior of electrons in solid-state crystals. But the same simple atoms, and what is the simplicity? That in order to see each other, they have to bump and collide. They have contact interactions. They don't experience interactions at a longer distance. But in the last couple years, we are entering in a new quantum revolution where actually we're able to trap and control more complex objects. So molecules, in this case we are talking about molecules made of 2 atoms, but these molecules made of 2 atoms have rich internal degrees of freedom. They have rotation, vibrations, hyperfine degrees of freedom. And moreover, they offer the possibility of having dipole-dipole interactions that allow me to 2 atoms interact at a distance. So this has been one direction that we have progressed, and not only in molecules, but we have also explored different types of atoms that have a large spin. And when they have large spin, they also have strong magnetic dipole-dipole interactions that act at a distance. Besides that, now there is the possibility of actually excite one electron in an atom to very high orbital, and this creates what is called a Rydberg atoms. Rydberg atoms have very, very strong van der Waals interactions, so strong that they have been proposed for doing quantum information. So they're offering powerful, important capabilities in order for quantum simulation and information. We are able to use photons to mediate the interactions in the of the atoms. So I told you atoms only talk to each other when they bump. However, if we put these atoms in an optical cavity, the photons, an atom can absorb a photon and emit a photon, and because of that, the atoms start to interact at a distance. And this is the field of cavity QED that is also trying to do quantum simulations. And finally, we are able to not only control neutral atoms, but also ions. So there are charged particles. They form a cell-ensemble crystal and also offer the possibility of having interactions that are even tunable by laser beams. So we are going to learn a little bit more of these systems in this talk, in this tutorial. So how is this control reflected in what we have done in the last couple of years? So in 2012, for example, the Nobel Prize has been given to Sir Harosh and David Wineland here at Nice for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. For the case of Dave, he was using ions. For the case of Sir Harosh, he was using photons. And what is the consequences of that? If you think about what are the state-of-the-art sensors, actually they are made with ultra-cold. They're mostly using ultra-cold particles, ultra-cold atoms. So we have the most precise atomic clocks. We have the most precise magnetometers to measure magnetic fields. And for example, even in Stanford, you have the best atom interferometer to measure gravitational potential and even starting to do connections with quantum gravity. In Mark Kasevich, there is a tower of 10 meters. He's dropping the atoms and trying to use the coherence even at such large distance to measure gravity. So this sounds really, really exciting. However, we are reaching the point that, well, we want more. And what is what we want more? We don't want to manipulate independent atoms. We want actually to manipulate correlated quantum matter. What is what we are going to gain when we understand these correlated systems? Well, we want to create powerful quantum simulators. So actually, many body systems are so complex. For example, solid-state materials are so complex that regardless of many, many years of research, for example, we don't understand the phenomenon of high-temperature superconductivity. We don't understand what is the essential physics that rule out the behavior of high-temperature superconductors. The hope is that by creating a system that is fully controllable with atomic systems and you can manipulate and actually engineer similar type of Hamiltonians, we can understand this phenomena and even create, for example, room temperature superconductors, quantum materials that are more advanced that nature naturally offer. Well, we want to create quantum computers, and we want to, of course, use the quantum supremacy for many, many different directions. And just to connect to this morning tutorial, actually, ultra-cold atoms might allow us to have a window, an understanding of fundamental physics, and try to simulate with the system the behavior of black holes. and understanding connections with quantum gravity, and even there are detectors of dark matter. And finally, we want to use correlated quantum systems to beat all possible quantum systems operated with classical, all possible systems that operated with uncorrelated particles, and create the most precise sensors possible in the world. So my hope in this tutorial is to tell you a little bit about connections first between quantum simulation and clocks. And later, I'm going to, in the second part of my talk, I'm going to touch more in the connection between quantum simulators and fundamental physics and prospects for emulating quantum gravity with these systems. Okay, you might ask how we are planning to accomplish such complicated tasks. And what is happening is that the experiments are progressing at a rate that is beautiful. It's very exciting. So the experiments are able to actually probe and see individual atoms now. So before, we were always measuring what happens on average. We took a picture of the whole systems. Now, there is the possibility of having what is called quantum gas microscope, where we are able to see individual atoms in an individual lattice site and control them and move it, so full control of individual particles. So this is a picture of a quantum gas microscope at Harvard. Each individual spots that you see there are atoms. So we want to see, we can see them and we can see how they move it in real time. The other possibility, and of course this is, initially it was at Harvard, there are many labs around the world that have these quantum gas microscopes. Now we can also control individual atoms by actually trapping them in microtraps. That is called optical tweezers. So you see this, we can create arrays of these tweezers. This is the tweezer, this is the atoms. And we can assemble them in 1-dimensional, 2-dimensional, 3-dimensionals. So we can take two atoms, make them close with the tweezers, entangle them, and then move it apart and keep them entangled. So this is one of the most exciting directions of how can we really can build a controllable quantum computer, for example, with these systems. Now we can also see in ion traps, we are able to resolve individual ions. So these dots are individual ions. And we can actually do gates that control at the single atom control. This is happening, for example, in JQI, NIST, Innsbruck, and very different labs. And we are reaching, before these systems were restricted to 7 ions. Now, actually, we have the latest experiments that have been able to actually cool down, even operate in a cool environment, are trying to reach arrays of 200 of ions. And without cryostat, they are reaching like 51 or something. So we are really progressing in that direction. And here at NIST, and this is going to be part of the next talk, we can trap 2D arrays up to 500 ions. And well, there are different types of having control over the atoms. One is, of course, spatial control, but also is energy, having the resolution capability to resolve very tiny energies. And this is what we are achieving in the next generation of optical lattice clocks here at GILA and NIST, who are able to resolve very, very tiny energies and hopefully have more understanding of the behavior of these atoms. So actually, the next part of this talk, I'm going to tell you a little bit about these optical lattice clocks and how these systems are not only allow us to measure time, but actually accessing beautiful many-body physics. So the interesting part is that this type of clocks doesn't have a pendulum, doesn't have a displays. They are made by atoms and light. So what I'm going to give you a picture is how these clocks operate here. To give you an idea of how precise these clocks are, I can make you an analogy. So it's a clock that doesn't gain or lose 1 second during the entire age of the universe, that are 15 billion years. That's how precise is this clock becoming, and actually we expect to be even 2 or 3 orders of magnitude better in the future. So how is that we are creating such a precise object? What is the requirements? Well, first, we want to use very good atoms. And actually, it ended up that atoms that have 2 outer electrons That means these atoms live in the second column of the periodic table, or others with similar structure, here like ytterbium, have been one of the best timekeepers. So these clocks operate in particular for this talk here at GILA with the strontium atoms. So you remember that atoms can be bosonic or fermionic. Actually, we will use fermionic atoms, and I will be clear later in the talk why fermions are better than bosons for timekeeping. And one partly also advantage of fermionic atoms is they have an additional nuclear spin that gives us another degrees of freedom for doing computation or for processing information. All right, so how does a clock operate? Well, it takes advantage of the quantized energy levels that we have in quantum mechanics to measure energy, and therefore energy is a measurement of frequency and therefore a measure of time. The advantage is that these quantized levels is universal. The quantization of energy is universal and is the same for an atom here or in China. So what we want to measure is very precise the energy splitting between two levels of an atom, two internal levels of an atom. So instead of a pendulum, what ticks in the clock is a laser or well, electromagnetic wave. That's what it gives the ticking of the clock. So what we want to do is that this electromagnetic wave tick at some frequency, and what we want is to log this frequency with the frequency of this transition. And to log the frequency of this laser to the frequency of the atoms, what we use is a feedback loop. And that's how a clock operates. That's the clock. So the atoms, we trap the atoms, and I'm going to tell you why it's important to trap the atoms. And then we do some mechanisms where we know when my laser is logged to the atomic transition, and there we know the frequency very precise. So it happens that this definition of the second in terms of the energy splitting of an atom is how dates back in the 1967, but the definition now and the current definition is based on the energy splitting of the cesium atoms. The point is that this definition is becoming obsolete, and actually the cesium clock is no longer the most precise clock in the world. And a simple picture of why the cesium clock is not the best can be seen by very simple analog of two rules, one that have more ticks, less ticks. So if I ask you which rule is more precise, then you are going to say B. Similar happens in the clock. More ticks, higher resolution. So the cesium clock actually operates with microwave. This transition is a microwave transition. So it operates at slower rate than what happens with optical clocks. That's the ones that I'm talking about in the second column of the periodic table. This energy splitting is optical, so we are talking about waves that are an optical wavelength. So they have 4 order of magnitude faster oscillations than the microwave. So that's why these optical clocks are better. But of course, well, I mean, yes. So let me tell you how better are those, what is the progress that these optical clocks are having in the last couple of years. So this is the fractional frequency uncertainty since the 60s to almost today. And you see that, well, really the cesium clock was the best that we had before. But you see the exponential growth in precision of this optical lattice clock and the ion clocks. So these clocks are uses optical transition, both the neutral atoms and the ions. But you can see that in the last couple years, actually this, this point is a point for the strontium, so not to be confused with the red color. It's reaching a sensitivity, as I mentioned before, of 2 × 10⁻18, becoming the best clock ever in the world. And why is that? It's because these neutral clocks interrogate many atoms at the same time instead of a single ion. That is how the ionic clocks operate. So we are going to, they not only allow us to interrogate, to have better signal to noise, but because we are interrogating many atoms at the same time, opens a window for understanding many body physics. So let's try to see that. In order to create a very good clock, we need a good atom, as I mentioned. We are talking about the alkaline atoms in the second column of the periodic table. And maybe you are wondering, why are those better? Well, they have an optical transition, but maybe other atoms can have also optical transitions. The important point is that the atoms in the alkaline atoms, like strontium, has an internal level structure where an optical transition have a very long-lived excited state. So this is an optical transition. You are seeing that the frequency is optical 10 to the 14 hertz. But this excited state can live more than 100 seconds. It's very, very stable. So this transition is kind of forbidden. And that means that the line width of this transition is just of the order of millihertz. So maybe these numbers don't mean anything to you, but maybe to make an analogy, if an atom were a pendulum, a classical pendulum, and you want to see how good this pendulum would oscillate, you are going to quote what is called a quality factor, that is the ratio between the frequency at which the pendulum is ticking divided by the damping rate. And if we do this for these atoms, we get that the quality factor is larger than 10 to the 17. So these atoms were able to make a pendulum that when one set, it will tick for the entire age of the universe without damping. That's the atoms, that's why we want these atoms. This is one part. But remember that the atoms are what we use to lock the laser. But if we really want to use the quality of these atoms, we should be able to make lasers that can be coherent for such a long time. And this is where progress has been very important here at GILA, that they are able to create lasers that have coherence times that are longer than seconds. So let me give you also an analogy of what that means. So I have a laser, and of course I can propagate it here in free space. And if you ask me how long a laser can propagate in free space without losing a single tick of the oscillations, then in this case, imagine that I'm going to be analogy of the laser with a tape, and I'm going to do a tape measurement. Actually, the laser could propagate from here to the moon, so there are around 10 to the 15, 10 to the 16 oscillations, and it will not miss a single one. So it's going to be a ruler that goes from there to the moon, and the ticks at which it remains coherent have a spacing that is less than the size of a bacteria. So it's going to be able to keep track of oscillation of this length. So that's what has been built here at GILA in Jun's group, and that's why his clock is reaching this kind of level of precision and accuracy. And finally, well, we have a good laser, we had good atoms. What else could it need to make a good clock? What would you think? Well, if the atoms are moving, for example, we are not going to be, the frequency that you will see from the atoms, if it's going to be modified by Doppler shifts. So you see that motion can modify the frequencies that you hear. So what we need to do is to trap the atoms very well. And this is where optical lattices have come into play. The idea is that not only we need to trap the atoms very tightly, so we need to illuminate them with laser beams, but we have to make sure that when we illuminate and trap the atoms, we don't disturb them very much. The point is that depending on the electronic level of the atoms, they can feel different trapping potentials. So what we have learned is that these strontium atoms, there is a particularly wavelength that is called magic wavelength, where the trapping potential for the two states is identical, so we don't perturb the transition. So we trap them very tightly and avoid Doppler shifts, but also we avoid all the type of systematics due to trapping and motion. So that's the combination of the three is what had led to the progress that we have now. Okay, so now let me go back to the feedback loop. So remember that we have the laser, we have the atoms, but we need to lock the laser to the atoms. And this feedback loop was proposed by Norm Ramsey. He got the Nobel Prize in 1989, and it's called Ramsey spectroscopy. And for that, we have to go back to quantum mechanics and imagine a two-level system. So a two-level system can have two levels, spin down and up. And what we do is that we start with this is the frequency that we want to measure, the energy split in between these two. So what we do to measure this is to generate a superposition between ground and excited state. So I don't know if you are used to this block picture, but in this block sphere, if you are in the ground state, you point down. If you are in the excited state, you point up. And if you are in a superposition of the two, you, for example, point on the equator. So what we do is that we illuminate these atoms with a laser, and we create the system in a superposition between ground and excited state. We generate coherences. The point now, if our laser, the frequency of the laser is not exactly the frequency of the atoms, then the atoms this spin is going to feel an effective magnetic field that is proportional to this difference in it's called the detuning. And a spin in a magnetic field is going to precess in a direction perpendicular to the magnetic field. So what happens is that this spin is going to precess at a rate that is determined by the detuning, and therefore this is the way that we can measure that. So you see how much phase we accumulate. This phase is measured by transferring the coherence into population para another pulse. We measure the number of atoms in the excited state. We see what is called a Ramsey fringe, and this Ramsey fringe oscillates with something that is proportional to the detuning. And by knowing that, this is the way that we can lock the laser with the transition frequency, and that's how we measure what is going on. This is the feedback mechanism that we use to lock lock the laser with the atoms. So everything looks great, very cool, but this, what I'm talking about here, is for a single atom. And the idea of this talk is that we want to understand many-body behavior, complex many-body behavior. In fact, what happens in the clock, is that the clock operates with many atoms. So what happens? Well, ideally, if you have many atoms, and if the atoms are not interacting at all, we win because we have a very large signal to noise. We have many copies of the atoms all doing the same thing together, and that's great. So remember, the atoms are trapped, in this case, in a 1D optical lattice where they form this type of pancakes. So this is the optical potential. There are many particles in each of these pancakes, but they are all ticking at the same time. That's the ideal case. However, along this direction, in this pancake, the atoms can move and they can collide with each other. And when we are bringing these atoms to very cold temperatures, what happens is that when they move and they collide, we have to understand these collisions also quantum mechanically, and quantum statistics is going to determine how the collision behaves. So what happens is that in quantum mechanics, collisions are always also quantized. And there are two, the quantization is characterized in terms of partial waves and symmetry of the collisions. And what happens is that, as in quantum mechanics, we define angular momentum operators associated with the partial wave of the collisions. We have the lowers that L equal to 0, and these L equal to 0 collisions don't have any barrier. The atoms can collide without energy cost. But as you go to L equal to 1, there is a centrifugal barrier that makes that these atoms that they are collide, there is a barrier that prevents the collisions to these atoms. So what happens, and this is where quantum statistics matters, is that fermions can, because they're identical, they cannot occupy the same internal state and at the same time, and therefore these S-wave collisions are ruled out and cannot happen for fermions, for fermionic particles. This fact that fermionic atoms cannot have the low energy collisions was one of the main appeal of clock makers to use fermionic atoms, because they said, okay, if I am ultra cold, I'm only going to be affected by these collisions that have no barrier, and if because atoms are identical, they cannot collide because of Pauli exclusion principle, then the only collisions that I can have are the L equal to 1 collisions that have a barrier, so it has some energy penalties and happens at very, very slow rate, because the energy barrier, for example, are the order of 30 microkelvin, where we are cooling the atoms below 1 microkelvin. So in principle, clock makers thought, Okay, that's great. Let's make our clock with fermionic atoms. Let's use the barrier. Let's forbid these collisions, and we have the perfect clock. We put as many atoms as we can, and we have a very large signal-to-noise ratio. Well, this actually didn't happen. When they created the first clock at GILA, they were using strontium atoms. They were looking at the ticks of the clock, and what they saw is that the clicks of the clock depend on the density of the system. So the more atoms, then they change, depending on the number of atoms, the tick that they saw was different. So collisions were playing a role. That was puzzling, but exciting at the same time. Puzzling because, well, we thought that these collisions were not important. They were very small. But exciting is that the clock was so sensitive that even these tiny collisions were affecting the clock ticking. So this opens a possibility to actually use atomic clocks to actually study many-body physics. So it's the perfect synergy with something that is ultra precise and can probe very, very tiny energies and long probing times, can probe for the same time physics associated with many body systems, including quantum magnetism and many other rich phenomena that I'm going to discuss. So I'm going to give you a cartoon of what we are trying to do with these clocks, with these very, very, very good clocks. So first imagine that you are a bad clock. And I'm going to ask you, what do you see? Imagine that your coherence time is very short, so you can only see for a very short time. What do you see? Again, what do you see? Now imagine that you are June and you build the optical lattice clock at GILA, and you can probe a many-body system for a very long time. Let me ask you, what do you see? What do you see? An edge, exactly. So that's the idea. So we want to use this clock, some glasses that allow us to probe very complicated many-body systems, to resolve them and understand their quantum behavior. That's the goal. That's what we are trying to do. All right, so when now you put your condensed matter hat and you ask yourself, what characterizes a strongly correlated behavior? Why make these very complex solid-state systems be that hard to solve? Then the answer is that they are rich because we have to deal with the interplay between different degrees of freedom. We have to control spin degrees of freedom, we have to control an orbital degree of freedom, and we can control the charge degrees of freedom. So electrons have charge, have orbital, and have spin degrees of freedom. Orbital angular momentum, spin, and charge degrees of freedom. And it's the complex interplay between of them that makes the physics so complicated. So the good news, and this is what I want to convey today, is that we can encode all these degrees of freedom in the same atom. So in strontium atoms, we can encode the spin degrees of freedom in the nuclear spin. We can encode an orbital degrees of freedom in the two clock states of the atoms. And lately, we have been able to make neutral atoms that doesn't have charge to behave as if they were charged particles. So we have all of this at the same time. So hopefully, this will allow us to achieve the dream that Richard Feynman postulated, that is the idea to make a quantum simulator. So we want to use these full controllable atoms in the long term to generate a quantum computer, and in the short term to generate a quantum simulator of strongly interacting condensed matter system. All right, so let me elaborate a little bit more in this idea of quantum simulation and the connections with the clock. And I'm going to give you a brief example of what we have achieved so far, and at the end of the talk, I'm going to tell you a little bit of how we are trying to also go up one step and try to see how we can use the clock as a quantum computer. All right, so the idea of quantum simulation, as I mentioned before, is that we want to use atoms to emulate the behavior of electrons, and we trap them in optical lattice that makes the role of solid-state crystals. So in principle, this sounds like a very, very good deal. However, it's true, but there are big challenges. What are the challenges? Well, the good part is that we have atomic system fully controllable. We have no defects, no disorder. There is the complex atmosphere of condensed matter systems. We don't have it. Our system is clean. We don't have defects, perfectly controllable. But there are two issues that are major constraints for us. One is that if you think about ion crystals, the lattice spacing of the order of angstrom, very tiny, atomic scale. Whereas, remember, these lattices are created with optical light, and therefore the spacing is micrometers. So it's order of magnitude, 3 or 4 order of magnitude larger than what you have in solid-state crystals. Second, atoms are much more heavier than electrons. So it can be like 5 order of magnitude heavier. And if you think about energy scales, what determines an energy scale of the system is the interparticle distance and the mass. And both of those conspire such that some phenomenon that happens at Kelvin temperature in solid-state systems, we have to go down below nanokelvins to see the same phenomenon in coalatoms. So even though we are experts in cooling down systems, we are not capable to cool down now, and it's only evolving to such cold temperatures. So that has been a big challenge for us in the last couple of years. However, there has been progress, and I'm going to tell you a little bit of the progress that we have made, and why in some situations, in order to see similar phenomena, we can actually be able to see phenomena at higher temperatures. So let me tell you first a little bit of a story of how we can generate a simulation of quantum magnetism in the clock, and how this simulator actually helped us to improve the clock significantly. So the idea, as I mentioned before, is that we have the atoms trapped in a 1D optical lattice. That means the atoms are so tight that they cannot move from one side to the other, so the lattice is along this direction. But along the transverse directions, they are not the trapping is only like an effective harmonic potential from the curvature of the laser beams. So inside, we can look at this pancake and think about as a two-dimensional harmonic oscillator. Here is in 1D, but imagine that you have a two-dimensional harmonic oscillator. And we have particles in this harmonic oscillator, and we want to understand how these particles collide and how this collision is going to affect the ticking of the clock. So let's see. So I mentioned that we are using nuclear spin polarized particles such that the only collision that is allowed is the one that have a big barrier, the big wave barrier. So the collisions are going to be suppressed. They are going to be tiny, but that's what we are going to use to model them. Sometimes if you have something that is small, you can do some type of perturbation theory to understand what is going on. So that's what happened. So you have this harmonic oscillator. The atoms are thermal with respect to this harmonic oscillator levels, so you occupy almost with a Boltzmann distribution these energy levels that are quantized, however. And now the point is that the frequency of the harmonic oscillator, that means the energy spacing between nearest neighbor levels, can be of the order of 500 hertz. And the interactions that we are measuring, that the clock can see, are as low as 1 hertz. Because of this P-wave barrier, the interaction, the collisions are suppressed. So what happens then is that because this energy is so small, then atoms cannot collide and change energy levels because it costs too much energy. The atoms, what is going on is that the atoms are going to be pinned kind of these harmonic oscillator levels. They cannot change the motional degrees of freedom because it costs too much energy. And the only thing that they can do is that they can change their spin degree of freedom. So they have a spin precession, for example, but they cannot move. So that means that we do have a lattice. So these harmonic oscillator levels can be thought as energy, as lattice sites, but in energy space. It's not a real lattice, but the atoms are pinned in these harmonic oscillator levels. And because only the spin degrees of freedom matter, then we can construct a model of how this atom interacts. The point is that you can see in this harmonic oscillator, the wave functions are delocalized. So there is these atoms in the harmonic oscillator functions are delocalized in space. And if they're delocalized in space, what happens is that an atom in this harmonic oscillator can interact with an atom in the other harmonic oscillator. So the interactions are kind of all-to-all. So this is very different to what you construct in condensed matter systems when the interactions are mostly local. These interactions can be that an atom here can interact with any other atom every other place. So, but the advantage here is that instead of worrying about what individual atom is doing, then we can write collective spin operators that is the sum of the spin of all of my particles. These are large spin operators. And then what we can write is an effective model, an effective Hamiltonian of how these harmonic oscillators tick with the clock laser. So as I mentioned before, the detuning acts as an effective magnetic field. So this is the term caused from single particle. But what you can model is that the effect of collisions enters as an interaction energy term, and this term can depend of the different collisional terms that determines the internal collisions. So I know this is a little bit, I'm not showing you how you get into this, but what I want to show you is that this very simple model of magnetism, a collective Ising model, can model how the atoms are ticking in the clock. So basically the idea, if you do this modeling, of that the Hamiltonian, the collisions are creating this type of SZ squared term, where the coefficients depends on the parameters of the collisions. What happens is that you imagine that if we are going to see how this is affecting the ticking of the clock, you focus on one atom, you do kind of what is called a mean field treatment, where the atom is talking with the other atoms on the mean. So what you do is that instead of treating this operator as a quadratic operator, you do a mean field approximation where this term is replaced by SC times the mean. And if you do that, you can see that the tuning, that is what we were wanted to measure, is affected by the number of atoms, by the difference of atoms between being in the excited or in the ground state. SC is the energy, is the operator that is the number of atoms in the excited minus the number of atoms in the ground state. That means that, and this SC is controlled by the initial pulse when we generate coherences. Remember, in the Ramsey sequence, we start with all atoms down, and then we create a superposition. Before I show you the superposition on the equator, but we can create any type of angle for the time that we first illuminate the atoms. So that means, and when the theory, with this very simple model, we can see that the ticking of the clock is going to be dependent linearly with the number of atoms that I excite. This is exactly what the theory predicts. This is exactly what the experiment saw. And the point is that the ticking of the atoms can be made to be zero. The modification of the ticking of the atoms due to the interactions can be made to be zero, and therefore we can operate the clock at a regime when they are not affected by these interactions. Is this clear, or it was very confusing, this part? Clear? Yes? All right, so this is just an example of how we can access very simple models of magnetism. We can use the clock, and also we can use this to try to actually operate the clock at the optimal spot where it's not affected by collisions. But let me now tell you a little bit more, how we can actually use these systems to actually go to a more richer type of behavior. And what is, we have been able to explore a new symmetry that was the dream of condensed matter theories, SUN, that is called SUN symmetry. And we are able to actually use this symmetry in the future to create very complex state of matter like a chiral spin liquids. So this is the idea. So the atoms have an spin, have the orbital degrees of freedom that are the two clock space states that I have explored so far. But what happens is that the atoms also have nuclear spins. And in the case of strontium, atoms have an internal manifold of to 10 nuclear spin levels. So the nuclear spin is 9½ that means that I have up to 10 different nuclear spins that I can access. In addition to the 2 clock states, in addition to the ground and the excited state, I can have these 2 different internal states. So I have the possibility to actually emulate a system that I have a very large nuclear spin. In principle, this can be very complicated system, very complicated. But actually, in strontium atoms, there is something that simplifies significantly the interactions of the atoms in the clock. And this is the fact that we are talking about the clock states have total electronic angular momentum equal to J equal to 0. So they don't have angular momentum. That's the characteristic of these atoms, and that's why the excited state lives so long. So the point is that if you have J equal to 0, then there is no interaction between the spin, the nuclear spin I, so there is a nuclear spin associated with the nucleus, and there is the orbital angular momentum, and because J equal to 0, there is no interactions. And what means is that when atoms collide, the collisions don't depend on the nuclear degree of freedom. So that means that if I have 2 atoms, I don't care about how the nuclear degrees of freedom are populated. I only care on the electronic degrees of freedom. That generates what is called an SUN symmetry in the collisions. And this SUN symmetry in the collisions, what it means is that there are conservation laws associated that can give rise to very strong constraints of how atoms can collide. So if I have 2 alkaline atoms and the atoms have 2 different nuclear spin states, when they collide, they cannot emerge in different nuclear spin states. They have to conserve the nuclear spins. That is one of the conservation laws imposed by SUN symmetry. And this N can be in strontium as large as 10. So what happens is that alkaline atoms can open a possibility to simulate SUN physics in these systems. That is no longer an idealization, but actual reality. So maybe I'm being a little bit more abstract with the concept of SUN, but maybe give you some context of when SUN appears. So in the context of high energy physics, for example, if you look at quarks, they are ruled by an SU3 symmetry because they have 3 flavors. Yes, and well, you have the quarks and the gluons too. So you have all the SU3 symmetry in these type of systems. Now, if you have a large n order parameter, you can use it as an expansion parameter. So if n is large, 1 over n can be used as an expansion parameter. And for theories in condensed matter, for example, even if the system is very strongly interacting, you have an additional parameter to extract and try to do calculations. And using this, for example, this kind of expansion, we were able to predict that if you put alkaline atoms in a 2D lattice and make them interact strongly, the ground state associated with the system can be what is called a chiral spin liquid. That is a type of state of matter that is analogous to the fractional quantum Hall effect. It has anionic statistics and actually can be used for creating a topological quantum computer that can be a way to be a very error-free. Can be protected because they are not sensitive to local disturbances. So, I mean, SUN symmetry can be a very interesting direction to pursue, and this is something that we are trying to explore currently in the clock. So maybe I'm going to jump a little bit, and well, we have measured this SUN symmetry in the atoms, but maybe let me jump into, only let me measure that we were able to measure this SUN symmetry. And when we measure this SUN symmetry, we receive an email from the person that does the publicity of the papers. We published this paper in Science. And then, I don't know if you are familiar with the series Big Bang Theory. So it seems that when we published this paper, then an ad appeared saying that according to the science working in the Big Bang Theory, all began with Sheldon's participation in GILA research, hoping to confirm via direct observation a spin symmetry theory in quantum physics. So according to this ad, Sheldon was going to come and talk with me and with June, and he was going to learn about the SUN symmetry. Okay, But so this is an additional direction that we are trying to explore, and I'm going to tell you a little bit more how we are going to later why this can be very exciting direction. But now let me jump a little bit and tell you a little bit more on how we are trying to make neutral atoms behave as charged particles. And this is what is called synthetic gauge fields. So we are trying to engineer an effective magnetic field and try to make particles that are neutral feel a Lorentz force. So the way that we are trying to do this is actually using lasers. So we are trying to use lasers to illuminate the particles and in a way that they behave as charged particles, one, or in a way that we are going to induce or they are going to feel what is called a spin-orbit coupling. So I'm going to elaborate a little bit more on that. All right, so let me give, yes?
What's a gauge field?
A gauge field is something, you can think a magnetic field, a gauge theory, something that has some special symmetries, but in this context, imagine that I'm going to generate magnetic fields, that's our electric fields in the system. So we are going to, yes, gauge fields, we are going to make the atoms as if they were feeling a magnetic field when they move. So imagine that when you have a charged particle in the presence of a magnetic field, and if they make a closed circle, they feel a magnetic flux. So we are going to make an atom, when it goes through a closed loop, feel effect also as if it were feeling an external magnetic field. So let me say that this type of implementation has started many years ago, and there has been very different labs around the world trying to use lasers to make particles like behave as charged objects. So there has been progress in rubidium, in sodium, potassium, lithium, even dysprosium and ytterbium, many different types of atoms. But the problem is that these type of systems have, when you illuminate the atoms with lasers, you can excite it to the excited states, and this excited state can decay. And when the excited state decay, what happens is that they can suffer a spontaneous emission that is a way to decohere the system. So the advantage, however, that we are trying to do using atoms in the clock is that they have such a long time that the heating caused from a spontaneous emission is very small. So we can create this type of effective magnetic fields and try to see interactions while they experience this type of magnetic fields. All right, so what is the mechanism that we are going to use to make the atoms in the clock feel an effective magnetic field? So remember that the atoms are trapped in this 1D lattice, and in each lattice. So before, what I was telling you is that it's kind of an array of pancakes with particles in each pancake. What we are going to do now is that we are going to allow the atoms quantum mechanically hop from this pancake to this other pancake. So we are allowing the particles to explore the full lattice by hopping. So what is the idea? So imagine that I have my atoms, and the atoms have two internal states, the ground and the excited state. And their atoms are going to, when the atom absorbs a photon from the laser to the excited state, they absorb a photon and go from the ground to excited state. But also imagine that the atoms can tunnel from one lattice size to the next. So what is the process? The idea is that when I illuminate my atoms with a laser, the phase of the laser is k times x. So the phase of the laser is k times x, with k being the wave vector of the laser and a is the lattice spacing. So what happens is that if I have an optical transition, this wave vector k can be very large and even comparable with the spacing between the atoms in the lattice. So that means that k times a is not something very small, but can be something of the order of pi, very large. So that means that there is a phase difference between the atom, the laser that is in this lattice site compared to the phase of the laser in this other lattice site. So we are imprinting a phase difference between the different lattice sites. And this phase difference is what is going to act as an effective flux. Why? So imagine that I have, this is the ground and this is the excited states. This is one lattice site and this is another lattice site. So what happens when an atom is going to move, is going to be illuminated by lasers and be in this type of geometry? So I start with an atom in one lattice site. Then the laser makes the atom absorbs a photon and goes from the ground to the excited state. And because it's in lattice site n equal to 1, it acquires a phase from the laser that is e to the phi. Now the atom can tunnel from this side to the other just by hopping. This is motion. There is therefore no phase accumulated when it goes from here to here. Now an atom can go emit a photon and go from the excited state to the ground state at this other lattice site. But because the phase of the laser changes from this side to this other lattice site, there is a phase difference phi. So if this was e to the I phi, this had no phase. And then it can hop around. So what happens is my atom has done a closed loop. It has moving in this trajectory, and the total phase accumulated has been phi. So in each trajectory around a loop, the atom is accumulating as a phase phi. And this can be felt. This is exactly what happens as if my particle were an electron in the presence of a magnetic field. It's going to accumulate a magnetic flux that is going to be proportional to the magnetic field times the area. So the interesting part is that when we do this with atoms, the flux that we accumulate is huge. It can be proportional to magnetic fields that are not accessible in the lab in solid state systems. It can be of the order of 1,000 Tesla. It's very huge. So we are able to create actually synthetic gauge fields just by illuminating the atoms with light. So this is one way that we are trying to explore, and then there is the idea of trying to, for example, implement the quantum Hall effect using ultra-cold atoms and simulating fractional, well, in the presence of interactions, the fractional Hall effect, and there is a lot of interest in these directions. But let me tell you also the other way that we can interpret how these atoms behave in the clock, and is the idea that we are implementing, we are generating a spin orbit coupling. So here, who knows about the spin orbit coupling? So this is an effect that couples the spin with coupling the electron spin and its motion, yes? And it happens even in the hydrogen atom. It's a relativistic effect. But this is also playing a major role in condensed matter systems, and this is, for example, one of the most important mechanisms that people are used to generate in spintronic devices. Actually, this is at the heart of what is called topological insulators in condensed matter systems. And lately, it has been very exciting because people have predicted that if you have a combination of a spin orbit coupling with a superconducting material, in the presence of a superconductor close by, then these systems in the spin orbit coupling by the proximity effect of a superconductor can engineer Majorana particles. And with these Majorana particles, in principle, you can create topological quantum computer. And for example, you have heard that Microsoft, for example, is trying to invest in this type of developments, trying to generate a quantum computer using Majorana particles. So what I'm going to tell you a little bit is that, well, in principle, we can engineer this type of physics in a fully controllable way in our ultra-cold atom systems. Okay, so if I have an atom in an optical lattice, it's going to have a dispersion relation. Yes, so if I have an atom in free space, the dispersion relation is just p squared over 2m, the characteristic parabolic behavior. When I have an atom in an optical lattice in a periodic potential, the dispersion relation is not p squared over 2m, but it acquires the form of a cosinusoidal function. So this is called, this should be here, Q. Q is the effective momentum of the particle in the lattice. It's called quasi-momentum, and this is the dispersion relation of the atoms in a lattice. Now it's a little bit modified. So the point is that the atoms in this lattice are going to move, and I have two internal states, the two clock states, the ground state and the excited state. And what we are able to do is that we are able to actually make the two potential identical. Remember that we are using what is called magic wave lattice, where the dispersion is the same for the two atoms. So now I take a laser and illuminate my clock laser with it, and let's see what happens. So if I have an atom in some quasi-momentum, this is the dispersion relation of my atoms in the ground state. Then I have the dispersion relation of the atoms in the excited state. When if I am the ground state atom and I absorb a photon from the laser, then if the photon is optical, I mean it has a large wavelength, wave vector k, is going to impart to me a large momentum. So k times a, the momentum, the wavelength of the laser k times a is as large as pi. So it means that I am going to the ground to the excited state, but I'm going to change my momentum from the momentum imparted by the laser photon. So I'm going to go from here to here as I absorb a photon. Yes? So the point is that I can do a gauge transformation. I can change very subtle my system without modifying the physics, just a unitary transformation. And what I can do is that I can do this translation of my dispersion relation. So you can see I have an atom that is connected between this quasi-momentum and another quasi-momentum that is different by the momentum imparted by the photon. So I can move my dispersion relation, and still I connecting the ground state with an atom with quasi-momentum QA plus 5, but now the coupling of the laser is diagonal. Yes, you can see that? So now I can generate a diagonal system when an atom in the ground state have a different dispersion relation, the atom in the excited state, and the difference is the phase that's imparted by the laser. So this is called a spin-orbit coupling. So this is a way that we can generate a spin-orbit coupling, because now I have, for each quasi-momentum, I can see my system as being a two-level system, the ground and the excited state, but they are coupled by an effective magnetic field, where the effective magnetic field has two components. The component along the x direction, that is translating my atoms from the ground to the excited state, and this strength is proportional to the laser Rabi frequency, but you see that the dispersion of the ground and the excited band are displaced, and therefore, depending on the momentum, the atoms have a different detuning. The detuning that the atoms feel, or the magnetic field along the z direction, depend on the quasi-momentum of the atom. So the rate at which this effective two-level system precesses is going to depend on the momentum. So this is the magnetic field, this is going to cause precession, and you see that this precession is actually completely determined by the momentum of the laser. So this is the way that we are engineering a spin-orbit coupling in our system, and you can see when you have these two levels are coupled by the laser, you can diagonalize them, and what happens is that the effective dispersion relation is going to be two bands, and it's going to depend strongly or depend significantly on the strength of the laser that I am illuminating. So if the laser is weak, then I just have a small crossing. If the laser is very strong, I modify significantly the dispersion relation. So, but the important part is that if you represent each of the quasi-momentums in a Bloch sphere, you see that the orientation of the magnetic field in this Bloch sphere along the z, so this is the x component and the z component, the magnitude of the magnetic field of the z component depends on the momentum. And that's what is called a spin motion locking, and introduces some phase that depends on the momentum theta, that's called chirality. So how we have been able to explore the spin orbit coupling in the clock? So you see that I imagine that I'm going to prepare my atoms in the ground band, and I want to transfer the atoms in the ground band to the excited state. So I have my atoms in the ground band, and I want to move them to the excited band, because now the two bands are displaced because of the spin-orbit coupling, then are only going to transfer the atoms at the energies when this band cross. But then if I'm going to add the detuning, that is the difference between two bands, there is going to be at some point where these bands stop crossing. And when these bands stop crossing, as I separate the detuning, there are going to be no longer possibility to transfer the atoms. So I'm going to change the total detuning, and at some point the bands not cross. So when I look at how, depending of the detuning, how atoms I can transfer from the ground to the excited state, I'm going to only transfer in a window of the tunings, and outside this window, I'm not longer able to transfer anything, and I have some singularities that at some points when the band cross and they're almost touching, there is called Van Gogh singularities. That is where the density of states diverge. So this is what the theory predicted that the experiments we're going to see. And actually, this is what they saw in the experiment. So they prepare all atoms in the ground state, then they apply a laser, and then they look at how many atoms were transferred from the ground to the excited state. And when they look at the number of excited state atoms, they see that the shape of the excitation depends strongly on the depth of the optical lattice. So the larger so here, you see that the effect of the spin-orbit coupling is going to be determining of the tunneling of the atoms. The more tunneling they have, the larger spin-orbit coupling they have. And what they see is that this width of the band was determined by the tunneling, and therefore the more, when they were transferring the atoms, they were able to see these, what is called Van Gogh singularities, that become broader as they make the lattice shallower. So that was one of the first observations of a spin-orbit coupling in the experiment. They could also do the following, that instead of blowing away all the atoms with a very strong laser, they could use a very weak laser and only transfer the atoms that are very close to the resonance. So they try to transfer atoms from the ground to the excited state, then blow away the remaining atoms from the excited state. And you can see, because the atoms close to the resonance has some specific momentum, they were able to filter out only atoms with a specific window of momentum. So then what happens is that atoms with a specific window of momentum can be tuned by changing the detuning of the laser, so they can choose atoms in this window or this window, so we can control the momentum of the atoms that were transferred. But also, because the momentum of the atoms that were transferred have different magnetic field because of the spin-orbit coupling, they were going to precess at a different rate. And that's why they saw. So depending on the momentum of the atoms that they started, they were going to precess at a different rate, and you can see this, that they observe in the precession at the atoms precess at a different rate. So, I mean, maybe I'm getting a little bit too technical, but what I'm just trying to see is that they were able to see a spin-orbit coupling in these systems in the clock. So that's one exciting direction. But let me now go to the new optical lattice clock that is not only operates in a 1D lattice, but now operates in a 3D lattice. And let me try to connect a little bit with what we want to envision for implementing a quantum computer. How we can try to use atoms in the clock to actually perform a quantum computer. Of course, this will going to happen in the next, not in the, well, it's a future prospect, but that's going to be the idea. The idea is that when we have atoms in a 3D lattice, we not only have very good energy resolution, but we are going to have a spatial resolution. That means that we are able to see the lattice site at which the atoms come from. So we are not only going to be able to have a very narrow sensitivity of energy, but also we are going to have very narrow sensitivity. We are going to see spatially resolve where the different atoms were coming from. So, so this will allow us, what we are going to try to use is that we are going to explore the physics of atoms in a 3D lattice and what is called the hover model. So when atoms are placed in a lattice, the behavior of the atoms is described by this so-called hover model. And this hover model is expected to be the model, for example, that explains the behavior of high temperature superconductors. So when you have the atoms in a 3D lattice, what are the characteristic energy terms in these systems? So the atoms can hop from one lattice side to the next. That is called the energy, so they can hop from one lattice side to the next. This is the tunneling. They can have interaction energy. If I have two atoms in the same lattice side, I can have an interaction energy U. And in general, there is another trapping potential that is a single energy term. So this seems to be the model that rules the behavior of high temperature superconductors. It's very simple to write. So you see that it only have a tunneling and an interaction energy. But actually, the physics of the hover model is very complex that no one at this moment knows what is the phase diagram of the hover model in 2 or higher dimensions. This model started to be implemented in ultra-cold atoms since 2008. And there has been very important developments in the last couple of years on how we are going to use these systems to emulate the behavior of electrons in solid-state crystals. So there is only a speculation of what is the phase diagram of the hover model. So it's believed that is something like you have something that is a phase that is the phase diagram is characterized by the hopping. So how many particles you have comparable with the number of lattice sites. So here, when you have zero hopping, means that you have one particle per lattice site. So exactly one atom per lattice site. And what is believed is that the model, the hover model, has antiferromagnetic phase at zero doping, but when you start to put holes and dope the system, you are going to enter a superfluid regime, so a superconducting regime that has some D-wave symmetry, and this is the idea. This is the behavior in principle that explains the behavior of high temperature superconductors. Still, it's not very clear if this is actually the phase diagram that determines the behavior of the system. So one of the questions that we have is that if we can use ultra-cold atoms to actually identify the phase diagram of the hover model. And well, there has been great progress, but still we are stuck at very high energy, high temperature, remember, because the difference in energy scales between condensed matter systems and atomic systems. But one part of the phase diagram that we have been able to see and explore is the case where there is no doping, where the system is antiferromagnetic. So how is this behavior emerging? What explains the antiferromagnetic behavior in the hover model? The antiferromagnetic behavior is explained in what is called super-exchange interactions. So let me tell you a little bit about super-exchange. And super-exchange is that if I have two atoms at separate lattice sites, their wave function in principle are not overlapping or very tiny. So I have one atom in one lattice site, an atom in the other lattice sites, and the question is how an atom in this lattice site is going to know about the existence of the atoms in the other lattice sites. So the idea is that even with a very tiny overlap between the wave functions, still one atom can know that there is another atom in the other lattice site and align their spin to minimize their energy. That's what is called super-exchange interactions. And actually, it's the same behavior that happens in solid-state materials and was introduced by Phil Anderson, or also the same behavior that rules out the behavior of a hydrogen molecule when you have two hydrogen molecules, so each one with one electron. So the question is how this electron knows the presence of the electron of the other hydrogen atom in the molecule. So the idea of super-exchange is quite simple. So let me explain you a little bit. So I have one atom in one well and another atom in the other well. And for example, imagine that this atom is spinning up and this other atom is spinning down. So the idea is that if the atoms are not talking, any configuration of the spin has low energy. But now imagine that this atom is able to tunnel from this lattice side to this. as the one atom tunnel from one lattice side to the other lattice side is going to have an energy cost U for tunneling. And therefore, it costs so much energy that it can only be a virtual process. It's just perturbation theory. So the atoms are going to go back because to remain with two atoms per side costs too much energy. So that means that we are creating the possibility of when one configuration up-down goes into the configuration with two atoms in the same side, and then by tunneling back, we have a coupling matrix elements between up-down or down-up. Similar happens if instead of this atom hopping to this side, the atom copies on the other side. So, but what happens is that if you have an energy state that is up-down, that has coupling with moment in energy up-down, the effective Hamiltonian that rules out the spin degrees of freedom of the system is in the form of an exchange Hamiltonian, S dot S. So what happens is that when we have these atoms in these lattices and experience these virtual hoppings, then the low energy system, the low energy state in the system is ruled out by the super exchange interactions that happens to have a plus sign when we are talking about fermions and a minus sign when we are talking about bosons. So S dot S is if you have a plus sign when you have two atoms in two internal degrees of freedom with a spin 1/2, there are 4 possible configurations that you can have. A spin singlet or a 3 spin triplets. What happens is that if you look at this Hamiltonian S dot S, the spin singlet is the one that has the lower energy. The spin singlet has the states anti-aligned, and this is what explains the antiferromagnetic behavior in the Hobart model. So the super exchange interactions, therefore, is what explains the antiferromagnetic behavior in the Hobart model. So what we want to do in the clock is trying to use these super exchange interactions to create gates or to create something that is, so we want to use atoms in an optical lattice with 2 internal degrees of freedom as qubits, and we want these atoms to use these atoms for computation. So how we can do that? So what we want to do, and that's in the near-term future, is we want to use super exchange interactions in the presence of a spin-orbit coupling to create highly entangled states, and a particular type of highly entangled states that are called cluster states. So cluster states are supposed to be some states that are useful for another type of way to do quantum information that is called one-way quantum computation. That is, you create a highly entangled state, and then the gates are created by measuring this state, this cluster state in the system. So the way that we can want to do is to have my atoms sitting in this 3D lattice. And then what we want to do is that we use a spin-orbit coupling coming from the laser, that's what I explained it before, to transform these super exchange interactions in a Hamiltonian that is the form SCSC. So what happens? So imagine that I have the wave vector of my laser K such that I adjust such that K times A is pi. K times A being pi means that the single particle Hamiltonian from the laser is staggered. So it has a phase that is +1 -1, and that means that the phase changes sign between nearest neighbor side. So I have a phase that is, for example, I have +C minus C plus C minus C. So the lower energy state in this system want to be anti-aligned, up, down, up, down, up, down, up, down. So the point is that if I have, so if you can see the ground state wants to be, for example, down, up, then the first excited state is when I flip one of the atoms here, for example, up, up, and down, down. They all have one spin flip. And the next excited state is when I have the particles up, down. So up, down, up, 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 down, down, and down, up. These are the lower energy states of my system. Now, but I can also have the process when one atom tunnels from here to experience the super exchange. So I have my atoms, they are frozen, but they can tunnel from one lattice side to the next. And what happens is that if they're in configuration that is up, down, when they tunnel, the energy caused because of the interactions is the energy difference of this configuration minus the energy difference of having two atoms in per lattice sites. When they are in this configuration, the energy is U minus omega, small. If omega is close to U, this configuration can have a small energy. However, these atoms that are up, up, and down, down cannot tunnel because Pauli exclusion principle doesn't allow me to have two atoms with the same spin in the same site. So this configuration will not tunnel at all. And this configuration can tunnel, but still is going to cause a lot of energy because the energy difference now is going to be U plus omega, and this can be very large. So the only configuration that is allowed to tunnel is the configuration when you have the up-down. So this is only configuration that can acquire a phase. The other is energy suppressed. And this is the way that we are transforming a Hamiltonian that is S dot S, where all the states could, in principle, tunnel, triplet and singlet, to a configuration that is the form SCSC. And this configuration of the form SCSC is, in principle, what can be used for cluster state generation. So the idea is that we are going to have my atoms in the clock, illuminated with the laser, adjust the phase of the laser to be pi. And then the idea is that we can implement this Hamiltonian to when you have all the atoms all pointing along X, this is the initial state. Then we illuminate the atoms in the clock, allow them to acquire a phase from the super exchange and the laser, and then we stop at a specific time where we create a phase gate between each pair of atoms, and this phase gate between each pair of atoms create what is called a cluster state, and this cluster state is a highly entangled state that can be useful for quantum information, and the utility is basically when I have dimensions 2 and higher. That's why I can create a universal quantum computer with this type of states. So, we can try to, and now if the clock start to have single-site addressability, in principle, we are able to actually create a cluster state and, in principle, to prepare the system for exploring a one-way quantum computer. I mean, this is still the future, but preliminary steps towards this goal are starting to be built in Jun's lab. So just to wrap on, I told you a lot of information today. I hope you got a little bit of the different directions that we are trying to explore with ultra-cold atoms in the clock. So what we have been able is, we saw atomic collisions in the clock. We saw that we can use these atoms, alkaline atoms, to exhibit quantum magnetism and exotic SUN symmetry. We were able to understand this complicated collision in the clock and control them to make the clock not feel any effects of interactions and operate at 10 to the minus 18. Using this clock as a quantum simulator, we were able to measure the SUN symmetry in the clock. Actually, combining all of these in 2015, the clock were able to become the best clock in the world in 2015. Then we were able to simulate synthetic gauge fields in the clock and open an avenue for actually exploring a little bit of the topological insulator, and in principle in the future trying to implement Majorana fermions in these systems. We have now the 3D quantum degenerated clock that is atoms enough with all the quantum degrees of freedom, all the levels, so a degenerate Fermi guys in a 3D lattice. And well, that's where we are now, and hopefully in the future we can really create these cluster states and we can use these systems for quantum simulation, for quantum computers, quantum technologies, and synthetic materials. So let me just say that there is a great vista ahead in my point of view with these systems, and let me acknowledge my collaboration with John G. He is going to give you a plenary lecture on Tuesday, I think it's Tuesday, and hopefully this tutorial could help you a little bit get some idea of what he's going to talk about and help you understand better his lecture. So with that, thank you very much, and we are going to be ready in the next lecture. I'm going to jump a little bit more on entanglement generation in atomic systems, and this second part is mainly focused in trap ions and how we can generate interesting states and some idea of how to explore quantum chaos and scrambling in trap ions. Thanks.